Hello YouTube! So in this video I'm going to mention a couple of important tree rules that you need to be aware of, and I'm also going to go through a little space saving method that I have. So 2 videos ago we saw this argument: if P then necessarily possibly P, and I want to look at it again using our original tree method. So we're in system B here, which means our accessibility relation is reflexive and symmetric. So we have the negation of our conclusion, and obviously since this is a false conditional we have a true antecedent and a false consequent. Now with the not necessarily here, we can open up a new world and derive not possibly P. Since accessibility is reflexive, W1 is accessible from itself, so we derive not P. Okay, so now what? Well, you might think to yourself, hey, we've got a symmetric accessibility relation. So since we have an arrow from WO to W1, that means we can draw an arrow from W1 to WO. Each world accesses the other. And indeed, that's right, that's fair enough. That's not wrong. And now you might think, well look, we have not possibly P here in W1. We can see that WO is accessible from W1, so let's put not P in WO, contradicting P and closing the tree. No, 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 no. You must not do this. The idea behind this is perfectly reasonable. WO is accessible from W1, and you can derive not P in WO from this not possibly P in W1, but you must not write it this way. Whenever you use a rule, you must place the result below the point at which the rule was applied. This is something I mentioned, I think, in my first videos on trees, and this rule applies in general, no matter what sort of system you're in. Whenever you use a rule, you must place the result below the point at which the rule was applied. Now, you might sort of think then, well, obviously this tree method is therefore inadequate for systems with a symmetrical relation. But there's actually a fairly easy solution. What we do is simply draw a new copy of WO, and it's the same world. It's called a continuation of WO, a continuation of WO, and then it's very simple. We simply derive not P in WO from this not possibly P, and that obviously contradicts P, so we close the tree. These are the same world. It's just a continuation of it, a new copy of it. So I think that's fairly simple. I mean, you just have to bear in mind, if you're doing bigger trees, you just got to sort of keep in mind which world is which, and keep track of your formulas. It's not really too difficult, that, but that's an important sort of rule to bear in mind, an important method there. Right, the next important tree rule can be illustrated by considering S5. So let's take this argument. Necessarily P or necessarily Q implies necessarily P or necessarily Q. Right, assume the premise and the negation of the conclusion. Now at this point all we can do is branch this disjunction here, and then since we've got necessarily P and necessarily Q, and it's reflexive, we then have P and Q, of course. Now we have this not necessarily, so on each branch we open up a new world and derive not necessarily P or necessarily Q. Okay, now you might think at this point, well, S5 trees are universal. Every world accesses every other world, so we can draw an arrow from W1 to W2 and of course back again. And indeed that works out if you check it, because W1 accesses WO, WO accesses W2. So by transitivity, W1 accesses W2, and the very same reasoning applies to W2 accessing W1. This is a huge mistake. This is a huge mistake. You must not do this. The reason is this branching here. Again, this is a rule that I think I mentioned before right at the start, and you've got to bear it in mind no matter what system you're in. Each branch of the tree is independent. You can't draw arrows between different branches. When we say that S5 is universal, that every world accesses every other world, that only applies if you're dealing with them on the same branch, as it were. Once you branch once you've branched and you've got two worlds on separate branches, they do not access each other. And that's sort of just a kind of absolute rule there. You must not connect those two worlds. Right. So let's just finish this argument off. We can derive P and W1 from necessarily P here, and then of course we've got this false disjunction, so not necessarily P and not necessarily Q. Now with the not necessarily P, we open up a new world and derive not P. Obviously from the necessarily P up here, we can derive P because these worlds access each other. So that's standard stuff, and obviously the same reasoning applies to this branch. Right then, obviously all these arrows do get very cumbersome, especially when you're in S5 and you've got every world accessing every other world. So let's consider the other tree method, and I want to have a look at an argument in S4. So we have this argument: if necessarily possibly P, then necessarily possibly P. S4 of course is reflexive and transitive. So we have the negation of our formula and we label it with our world. Now this is the little space-saving method that I sometimes use. Since, especially in PowerPoint, space is somewhat limited, and since I want to focus on transitivity here, what I'm going to do is put the reflexive rules along the side, like this. I'm going to put them all along the side here. Obviously, this isn't formally accurate, but I'm sure you'll see how it all fits together, and as long as you kind of pay attention to how you keep in mind how it fits with the main bit of the tree, then it works fine. So all the reflexive rules are going to be stacked along the side here, and the first reflexive rule is that 0 is accessible from 0. So we have our false conditional, so we've got a true antecedent and a false consequent. And of course, since we're reflexive, we can derive possibly P from this necessarily possibly P. And I'm going to put that at the side here, just right next to it like that. Now, we can then use this not necessarily to open up a new world, with not possibly, necessarily, so on. And here we have not possibly, so reflexivity immediately gives us this. Okay, we have necessarily possibly P up here in 0, so we can derive possibly P in our new world. And now we can use this possibly P to open up yet another world. Okay, now notice we have world 1 is accessible from world 0 and world 2 is accessible from world 1. Recall the rule for transitivity. If we have y is accessible from x and z is accessible from y, then z is accessible from x. So we can derive from this that world 0 here accesses world 2. Right then, we used possibly P to open this new world, so we derive P. And we can also use this not possibly necessarily up here to derive not necessarily possibly P in world 2. Now we have to use this not necessarily to open up yet another world, world 3. So 1 accesses 2 and 2 accesses 3. This means 1 accesses 3. Also 0 accesses 2 and 0 accesses 3. So 0 accesses 3. Okay, we had not necessarily possibly P, so we have not possibly P, and due to reflexivity of course not P. Now we're in a position to derive a contradiction. because way up here in world 0 we had necessarily possibly p, and since world 3 is accessible from world 0, we can derive possibly p, which contradicts not possibly p and closes the tree. Okay, I hope you see how that works. I sometimes like to stack formulas at the side like that, especially when I'm doing reflexive trees. It really does help to save space, and it allows you to, I think, more easily keep track of which rules you've applied. But you do have to be careful, you know, not to get mixed up, especially if you start branching. This is all obviously just along one branch on the same tree. Okay, well, I hope that was helpful. We'll, I suppose, be doing some invalid formulas next time. Thanks for watching. Goodbye.